Okay, so let's get started. We're going to be talking about the molecular orbitals of a heteronuclear diatomic molecule. We've just been focusing previously on homonuclear diatomic molecules, which means in this case, we're going to have different elements in our diatomic molecule. So for instance, let's try nitric oxide. Now, when we develop our molecular orbitals, the first thing we need to remember is that the more electronegative atom has a lower energy. So when we do this, let's go ahead and go to the next page. What we'll be doing is, let's go ahead and start with the 2s. And the 2p. Now for the s's, what we'll do is we'll take our electronegative atom and we'll go ahead and lower the energy on that. Okay, and likewise with the 2p, we'll also lower the energy. So for nitric oxide, the nitrogen will be on the left-hand side and the oxygen will be on the right-hand side. And of course, on our y-axis, this is energy. Okay, so now when we develop our sigma and pi bonds, now we have to know whether or not we have a strong sp interaction or a weak sp interaction. And in this case, this is a weak. Let me just write it in the center. We're going to have a weak sp interaction, which means when we have a weak sp interaction, let me just rewrite this so it's s and p separately. Sp interaction. So when we do write this, then we'll just write it like we normally do. We have our sigma here. This is 2s, 2s. And then with the equal amount of energy for the sigma star 2s, 2s. Okay, I think these are a little bit too crunched up, so let me smooth this up a little bit more. And the 2p. So in this case, when I generate my sigma 2p, 2p, and then I have my pi 2p, 2p. Each one of them is my pi 2p, 2p. I'll just one center. Okay. And then we'll have our pi star. The star. That's fine. Pi star 2p, 2p. And then my sigma star. Should make sure I have equal energy above. So hold on a second. Let me get that up. And my sigma star. Let's see. Pi star. Gotta make sure my energies look reasonable. So pi star P2P and my sigma star 2P2. Okay. And there's a bit of asymmetry to this. You find that the lower energy sigma is closer to the lower energy 2s orbital. The higher energy sigma star is closer to the higher energy 2s. Okay. Now for nitrogen, it's 1s2, and then we know it's 2s2. And then 2p3 for oxygen. It's 1s2, 2s2, 2p4. So we now have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons to use in our molecular orbital. So I have 1, 2, 3, 4, 5, 6. Remember, I'm going to pair these because that's the lower energy, but my pi 2p2p's are degenerate. So 7, 8, 9, 10, and 11. 2, 4, 6, 8, 10, 11. So what we find is that nitric oxide is a radical because I have an unpaired electron. This is paramagnetic because paramagnetic means is a property that your substance is attracted to a magnetic field. And this occurs because you have an unpaired electron. Diamagnetic means that all of your electrons are paired. So paramagnetic, again, your substance is attracted to a magnetic field. Okay. What else can we determine from our molecular orbital? That when we look at it, at our structure, it turns out that the radical electron is more likely to be on the nitrogen. Okay, 2, 4, 6, 8, 10, 11. Another thing we can determine is bonding order. So that's going to be equal to 1/2 of my bonding electrons. And in our diagram, we have 1, 2, 3, 4, 5, 6, 7, 8. Minus 1/2 of our non-bonding electrons, and I have 1, 2, 3. Gives me 5/2. So it turns out when you look at the structure for nitrous oxide, it's actually 2.5 bonds between my nitrogen and oxygen. And we can see that represented by a shorter bond length than you normally would expect with the double bond. Okay, so from our molecular orbital diagram of nitric oxide, we can determine that nitric oxide is a radical, it's paramagnetic, and the bond order is 2.5 bonds between the nitrogen and the oxygen. All right, so that's how we treat basically heteronuclear diatomic molecular compounds, that the more electronegative atom has a lower energy when we draw our diagram. Okay,